Okay, let's take a look at example 6. The set X consisting of the non-negative coordinate axes in R3. So what are they talking about? Here. So this is the non-negative y-axis. This is the non-negative x-axis. This is the non-negative z-axis. So what about this set? In other words, just the points on this part of the axis, this part of the axis, this part of the axis. It's a kind of peculiar set, but it is a set of points. But they say that it's closed because the boundary of X, remember that in order for it to be closed, the boundary of the set has to be within the set. And actually, the boundary of every point in the set is a boundary point, right? If you take a sphere and put it around any point on, say, this axis, then that sphere is always, no matter what the size of the sphere, it's always going to contain some points that are not in the axis and some points that are in the axis, right? So that's exactly what we mean by a boundary point. So every point in the set is a boundary point. So, and there are no other boundary points, so it contains all its boundary points. Therefore, we call it closed. Next, they say, consider this one. So what about this one? This is in R2, and this we're restricting X to be between 0 and 1, so I guess between 0 and 1, and we're restricting Y to be between 0 and 1. But if we look carefully, this says X can be equal to 0, so that means we can have any point on this y-axis, because all those points have X equal to 0, and I mean any point from here to here, and it also says the same thing about Y, so we can have any point from here to here on this axis is also included, whereas these don't have equal sign, doesn't have equal sign, so these points are not included. So we have this kind of rectangular region, but it includes this edge, but does not include this edge and this edge. So what about it? Is it closed or open? Well, here, this is a boundary point that's contained in the set. This is a boundary point that's contained in the set. We might start to think that it's closed because it contains its boundary points. But if we check here, this is also a boundary point, but it's not contained in the set, so it doesn't contain all of its boundary points. So that means that it's not closed. But is it open? It's going to turn out not to be open either. So it doesn't. So the point here is that a set doesn't have to be open or closed. Going back to the definition of open, a set X is said to be open if for each point X in the set, there's some open ball centered at X that lies entirely within X. Well, take a point, say this one. Is there a circle around this point that is entirely within X? No. So this point would not satisfy that condition. So the set is not open or closed. Okay, let's consider the geometric interpretation of a limit. So we're going to suppose that we have a function from Rn to Rm, where the domain of that function is some subset of Rn. And we want to say, what does this mean? So we want to think about it geometrically. So we're going to use the sort of technical definition that we sort of skipped over before, but we can see it very easily here. So that is, the technical definition says something like this, says, given any epsilon greater than 0, you can find a corresponding delta greater than 0. So, okay, so it looks a little confusing. So let's look at this picture. So what it's saying is, so we want to say that the limit of f as x gets close to a is equal to L. Okay, so we're going to picture this in 3 dimensions. but we're not really restricted to 3 dimensions. We can have n and m, but let's do it in 3 dimensions. So let's assume that the domain is within R2, and the range is just R. Okay, so that we can picture it in 3 dimensions. So, okay, so the domain is called X, and it's in R2, so it's something in R2, like maybe this, and the range is going to be the 3rd dimension in a 3-dimensional picture. It's going to be the height. So what we're saying is that looking at this, given any epsilon greater than, you can find this. So here's the epsilon. So what we're trying to say is that if we're given an epsilon around the supposed limit L, so the epsilon will define a sphere, or we call it an epsilon ball. So given an open ball, B sub epsilon here, centered at L, we can always find a corresponding B delta, a corresponding ball B sub delta over here, so that every point in B sub delta intersect X, so every point, where is B sub delta intersect X? It's right here, this stuff here. So we want to say that every point in there will be mapped into this ball. So we're given a ball. Can we find a radius delta around A so that everything within that ball here will get mapped into the given epsilon ball over here? And that is, no matter how small we make this ball here, suppose I make it like this, so I want everything to be really close to L. So can I find a small enough ball over here so that everything in there, everything within the ball that's intersecting X, will be mapped into here? And then, okay, I'm trying to say that the limit is L, so that means, can I get even closer to L? So can I make an even smaller ball around L? Can I then find a disk around A such that everything in that disk gets mapped into this really tiny epsilon ball? And then we say, okay, well, can we get even closer to L? So the point is that no matter how close we need to get to L, we can find a radius here, or a delta ball here, so that everything in that delta ball gets mapped into here. So that's a kind of geometric interpretation of what we mean by the limit. So it has to do with this epsilon sphere, or epsilon, what do they call it? Epsilon, I guess they call it an open ball. So they call it an epsilon ball, and we talk about a delta, what do they call that? Also a ball? Yeah, delta ball. Okay, but one of them is more like a sphere. But in any case, the idea is that if we want to get really close to L, we can make this small enough so that everything in there gets mapped within this small ball or sphere around L. If we can do that for any epsilon, then we call L the limit as X approaches A. So that's a kind of geometric interpretation of what we mean by the limit, especially in the case of R2 to R, but we can sort of imagine more generally what it means for from Rn to Rm. Or I shouldn't say we can imagine it, but we can understand it. Okay, so she says one thing. She says, we remark that for this definition to make sense, the point A here must be such that every neighborhood of it in Rn contains points X in X distinct from A. And she says such a point A is called an accumulation point of X. So an accumulation point of X is a point so that every neighborhood of it contains points in X. So suppose we defined X to be this set here, plus one more point out here. So this point out here would not be called an accumulation point. Because, of course, if you draw a really big ball around it, you will contain points of X. But there are plenty of smaller balls around it that you can draw, plenty of smaller neighborhoods around it that don't contain any points of X. So then we can't really talk about the limit as X gets close to this point, because there are no points that get close to it. It's separated from the rest of X. So it's not an accumulation point. So we don't talk about limits at points that are not accumulation points. She says technically this assumption should also be made in definition 2.2. A point A in X is called an isolated point of X if it's not an accumulation point. That is, if there's some neighborhood of A in Rn containing no points of X other than A. So like we said, if you have a point out here, there are going to be neighborhoods around it that contain no other points of X. So this kind of point is called an isolated point. So she says, from these considerations, we can see that the statement, the limit as X approaches A of f of X equals L, really does mean that as X moves towards A, so as we get points X getting closer and closer to A, f of X moves towards L. The significance of the open ball geometry is that entirely arbitrary motion is allowed. Okay, let's take a look at example 8. So suppose we have a function from R2 minus the origin. So it's all of R2 is the domain, except the origin is not included in the domain, to R. So basically we have a function from the plane to R, but we're not worried about or not considering the origin as part of the domain of the function. So suppose the function is this function here. So since it's from R2, it should be have two arguments. So we have the two arguments, and this is the function. So we can see one reason why we don't want to have the origin in the domain is because if we had the origin, then this bottom part would be 0. We don't want that. So she says, let's see what happens to f as X approaches the origin. Note that f is undefined at the origin, although this is of no consequence insofar as evaluating limits is concerned. Okay, remember that the limit as X approaches the origin is different than the value at the origin. So just because the limit is undefined, just because the function is undefined at 0 doesn't mean that we can't talk about the limit as we get close to 0. Okay, so we're going to think about what happens as we get close to the origin along different paths. So one path we could approach the origin along is along y equals 0. So y equals 0 means we're on the x-axis, so we're coming in this direction, we're coming in from this direction. And we're asking, what does the function look like as we do that? Is there a pattern? What does it look like? Well, therefore y is always 0 on this path, so we can replace y by 0. So we get this and this. And then we see that we just, at every point on this x-axis, on this line here, when y is 0, we get just x squared over x squared. So it's always equal to 1. Thus, as x approaches 0, along the line y equals 0, the values of f remain constant, and so we can say the limit as x approaches 0 along y equals 0 is just 1, because it's always 1. That means the limit is 1. Along the y-axis, however, so when x is equal to 0, then what happens? Then this is 0 and this is 0, and therefore we're getting 0 and 0, we're getting minus 1. So the limit as we approach on this path is different than the limit as we approach the origin on this path. So here we would write the limit as x approaches 0, but before we said along y equals 0, now we're saying along x equals 0, and now it's equal to negative 1. Okay, so that's interesting. So then we could ask, how about along other paths? How about if we came along a 45-degree angle? What's that going to look like? Is that, we actually have no idea what that's going to be, right? But when x approaches along a path that's defined by, say, y equals mx, right? We can have a path like this, we could have a path like this, but we could have a path, any path through the origin, and that could be, and if we're talking about straight line paths, for example, so what's the equation of a straight line through the origin? It's just y equals mx. So if we're talking about straight line paths through the origin, we're not limited to straight line paths. We could consider all kinds of other paths as well. But right now, let's just consider straight line paths through the origin, which would then be defined by, the path would be defined by y equals mx. So indeed, the value of f is constant along each line through the origin. So we saw that through this line to the origin, it was constant and equal to 1. We saw this line, it was constant and equal to negative 1. Now she's saying that through any line to the origin, it's going to be constant. They're not all going to be the same, as we saw these two weren't the same. But suppose we approach the origin through the line y equals mx, then then we can replace y by mx. So here we had y squared, so this would be mx squared, which is m squared x squared. Same thing here. Do some algebra here, end up with that. So now the limit as x approaches 0, for this, where we're given a particular path defined by y equals mx, so m is a constant, then this is what we get. And so we can see that the limit will depend on which line we're coming in to the origin from or through. It's going to give us different limits depending on m. So therefore, we say that if we don't get a unique limit, and already we know that we didn't get a unique limit because we got 1 in the case of going this way and negative 1 in the case of this way, but even for all these paths, we get many other values. Every path, every angle that we approach the origin from gives us a different m. We get basically an infinite number of values for what the limit will be, depending on the path by which we approach the origin. Okay, so as a result, the limit of f as x approaches 0 does not exist, because for the limit to exist, there has to be only one value, and here we see there's an infinite number of values. Since f has different limiting values depending on which direction we approach the origin. That is, no matter how close we come to the origin, we can find points x such that f of x is not near any number L. So remember, we're looking for a single number L, and no, there's not going to be a single number, and there's an infinite number of numbers. that it's going to be. So that we're never going to be able to say, oh, well, if we get really close to the origin, we draw a circle around it, that every point in that circle is going to be close to some given L. No, because there's going to be many, many different values that it's going to be close to, no matter how small this ball. So because of that, you might say, well, what in the world does this graph look like? So you might say, well, what in the world does this graph look like? Now, one thing to point out here is that think about these values. So, okay, by the way, what is M if we're talking about approaching it along this path? So then M is 0, right? The slope of this line is 0, so M is 0. So what does that mean? We're going to get we said that the limit is going to be this. So what is that? That's M is 0, so it's 1 over 1, which is what we said. What if we're approaching in this direction? Then M is, oh, whoops, we can't do M in that case because M is infinite. But any other M, let's think about what this means for any other M. So we can see that it's going to be 1 minus M squared and 1 plus M squared. So I guess we can always say that this is going to be bigger than this. So then we can say that the limit is going to be somewhere between -1 and 1. Okay, so anyway, that's what the limit's going to be. So we might say, well, what in the world does this graph look like at the origin? Because it's behaving so strangely. When you approach from one direction, you get one limit. When you approach from another direction, you get another limit. So here's a picture. So it's pretty hard to see what's going on here, but we can definitely see that it has strange behavior. So this is the graph, and it looks strange. Okay, then she gives us a warning. She says when we think about this example that we just did, it might lead you to think that we can establish what the limit is by showing that the values of f as x approaches a along straight line paths all tend towards the same value. Because that definitely didn't happen in the last example, but suppose we could show that if you come in to the origin or to some point A, and you consider all linear paths, all straight line paths, and they all go to the same number, which definitely didn't happen before, but if it did, then maybe we can conclude that that whatever that number was, in this case, if we call it L, that's the limit. She says, although this is certainly good evidence that the limit should be L, it's not conclusive. It's by no means conclusive. See example 23 for an example that shows what can happen. Okay, so she says, let's go back to this example again. Let's try to think about it in a different way. Let's try to write this in terms of polar coordinates. Who knows who thought of doing this? Probably someone was, well, whatever. Anyway, so someone thought of doing this. So let's follow through on that, see what happens. So remember, for polar coordinates, we write that x equals r cosine theta and y equals r sine theta. So using the Pythagorean identity and the double angle formula for cosine, we obtain, okay, so this is so here we start out with this, then we write this and this because we just said that x is this and y is that, so we get all of this. I guess we factor out r squared, and then I don't know where this comes from. I guess this is minus. So maybe there's a form, I guess this top thing equals this. So I can't remember such a formula, but maybe it's true. And the bottom one is easier to remember because this is, the r squared and the r squared cancel. And so maybe this inside the brackets is equal to that. And then this one is easier to remember. This is just 1. Or even if you don't remember it, you can check it. Cosine squared theta plus the sine squared theta equals 1. So finally we get, when we do this, and we decided, hey, let's think about this using polar coordinates. So we get that our function is equal to 2 cosine theta. That is, and remember, we've restricted the origin from being part of the domain, and one way to say that is that r is not equal to 0. So for r not equal to 0, f of xy is f of this comma this is equal to that. Moreover, to evaluate the limit as xy approaches the origin, we only must have r approach 0. So that doesn't specify a particular path. There can be many different paths. So if we prove something about when r approaches 0, we're proving something about all paths to the origin. And we're not going to put any restriction on theta, so it can be any angle and any possible path to the origin, as long as r is getting closer to 0, as long as the point is getting closer to the origin. So when we do that, we want xy going to 0, 0 of this function, means r is going to 0 of this function, and the answer is that as r goes to this function doesn't have r in it. So with respect to r, this is unchanged. When r changes, this does not change. So it's just equal to cosine 2 theta. So the answer is cosine 2 theta. So is that right? Well, we already found the limit for various paths. So let's go back to one of the easier ones. So we took the path, this path, and that was when y was equal to 0. We found that that was 1. Well, now we found a different expression. That is, we found the limit is equal to cosine 2 theta, but when we're talking about approaching the origin along the y-axis, that means that theta is equal to 0. So in that case, it's the cosine of 0, which is 1, which is what we said. So at least for that one path, this seems to be correct. So she says when theta equals 0, which defines the x-axis, then we get 1. And we take a different path. If theta equals pi over 4, which defines the line y equals x, then we get cosine of pi over 4. Cosine of pi, 2 times pi over 4, which is pi over 2, which is 0. So that one we didn't do before, but now we've done it rather easily by converting everything to polar coordinates. So again, anyway, the limit is equal to cosine 2 theta. So this is thus, as in example 8, we see that the limit fails to exist because it depends on theta, so there's not a single value for all possible paths to the origin. Okay, let's continue. Example 10. We'll do polar coordinates to investigate this function. So this one still has the same denominator as before, right? Yep, same denominator as before, x squared plus y squared, but the numerator is different. It's this. Okay, so we're going to use polar coordinates So we can go through this algebra. They rewrite this with polar coordinates here, here, here. And apparently you get this. Now this one does depend on R. The final result depends on R, whereas before the final result did not have an R in it. So this one does. Then they point out that the cosine of theta is always between -1 and 1, which implies that cosine cubed theta plus r squared cosine 5 theta is always going to be between this and this, because the biggest that this can be is, biggest that cosine theta can be is 1. So if it's 1 here, it's also 1 here, because cubing 1 and raising 1 to the 5th is still 1. So we get 1 plus, the largest this can be is 1 plus r squared. That's what they have here. And the smallest that this can be is if the cosine of theta is equal to -1, then the cube is still -1, and raising it to the 5th is still -1. So this is -1 minus r squared. So this thing is going to be bounded by these two expressions. So our function here, f, is this thing, that is this thing, times r. So our function is going to be bounded by r and this thing times, why is it, oh, times r. So we get that. So now we have an expression, kind of a bound on our function, and we want to add, we're asking as we approach 0, 0, which means as r goes to 0. So, well, remember that our function is always going to be bounded by these two things, or sort of be squeezed in between these two things, and we can see that as r goes to 0, this goes to 0, and this also goes to 0. So that means as r goes to 0, our function is going to be between 0 and 0. Well, that means it's 0. So they say, as r goes to 0, both expressions approach 0. Hence, we conclude that the limit is 0, since f is squeezed between two expressions with the same limit. Okay, let's stop here, and then we'll go on to properties of limits. We get these theorems, which make doing limits much easier. Now remember, why we're doing all this with limits is because we want to do derivatives. And we want to do derivatives because we want actually eventually to get to the concept of the gradient descent algorithm.